Hello, welcome back to the channel. This is Kasra. I'm going to show you in this Fusion 360 software how this machine that I'm designing will look like eventually. I thought that it's necessary that we go through all the little details about how this machine is put together and how it will work. So let's start with a few basics and facts. This machine is a compact 5-axis machine. All the moving parts apart from the A and C axis are made from granite, which have been machined and lapped and assembled together. And the reason for granite is because it gives me very good vibration dampening characteristics, as well as very good precision assembly. The rotating axes are made from aluminium, and I will go through the reasoning behind that as well. I spent over 2.5 years, I would say, designing this machine. Maybe 1 or 2 hours a day, sometimes a few hours over the weekend. Usually in the evenings every day I spent about an hour putting this assembly together. Obviously this is not the first version. I've been through multiple versions, and this is the one that I've decided to actually put together and manufacture. Okay, let's start with the basics. So it has I would say a stand, which I will show it to you now. So this part on the bottom is just a metal frame that's been fabricated together. There are some live videos on the channel showing how I actually put this fabrication together. It's just a metal stand. There's nothing interesting really about it. It is isolated from all the moving parts up top, so it's only holding the assembly of the machine and elevating it from the ground. So that's what it does. It's a relatively sturdy stand, and it's placed on these 4 casters, and these are they have a sort of a anti-vibration pad that you can rise them up by rotating these knobs, or you can lower them down, or actually in this case bring them up so that it will sit on these wheels. And these have bearings inside, and there's also a large bearing up top here. So it allows you to move the whole machine freely. And then once you are in place, then you will bring these feet down and you can level the machine as well. So that's how the stand looks like. Then we've got what I have named the bed assembly. Now the bed assembly of the machine, I can probably just get rid of all of that and then just show you this one. Well, I probably should just turn the others off. I think it works better like this. Right. You don't need to see these as well. Okay. The bed assembly, as I said, the main part is from granite stone. Then we've got these 2 granite parallels. So this top face has been lapped, this front face has been lapped, and this rear face has been lapped as well. So these are 90 degrees to the top face. And then we install these rails, which are quite interesting rails because they look like your usual X arrangement linear guideway with ball bearings that's been cut in half. And we've got 2 of these. So these are a special type of rail that would allow you to have an adjustable preload, which can increase rigidity and accuracy. The actual rail itself is also pretty accurate, so that means the profile has been ground very, very accurately. I think I've got the reports for this particular rail, 600 millimeters long, and for example, the distance or the thickness of the rail from this end to that end is better than zero point 0.3 micron, something like that. And they come in pairs, so they machine these both together and grind them together. So they are pretty accurate stuff. The manufacturer is THK. It's a very well-known Japanese brand. Then we've got a ball screw in the middle. So this is a C0 double nut preloaded ball screw, ground obviously ball screw, 15 millimeter diameter, and the lead is 10 millimeters. So by rotating the ball screw shaft, the nut will move by 10 millimeters each time. And then we've got these housings for the bearings, the bearing housing of the ball screw, the support bearings. We've got a flange type over here and the flange type over there. And these, all these metal parts are stainless steel. They've been machined, welded together, stress relieved, and then ground to a very good perpendicularity. Then we've got this brackets, which is machined from one piece of aluminium. Then we've got these couplings, which is actually the wrong type of coupling that I actually used. It's not a disc coupling, it's a bellows coupling that I've used, but I haven't really changed it on the design. Then we've got a 1 kilowatt 6000 RPM servo motor from Beckhoff with absolute encoders. Or an encoder rather. Then we have a Renishaw absolute linear scale over here. We also have these aluminium pieces, this one and that one, and what these do is they have a cooling channel. So the idea is to cool the whole rail down and keep the temperature controlled. So they have an O-ring that goes around, and then we've got an inlet, an outlet for water that goes through this, cool this middle piece down, which is a stainless steel piece, and then the rail as well. So that's your bed. Then on the front side of the bed, we have a couple of other plates. Then we have this sort of fixed table, which you have T-slots. And there's another chuck there. There is a Renishaw NCPCB laser tool setter or non-contact tool setter, which is pretty accurate. I think repeatability of this is about 0.5 micron. So that's for your tool presetting. It's only for small tools, but obviously this is a small machine, so it's quite good. Then we have the X-axis assembly. So this one is again another piece of granite, which is this one. Then we have the linear blocks. So these are your linear blocks for those special type of rails. Then we have the ball screw nut, the housing of the ball screw. Then we have another cooling pad to cool down the actual ball screw nut. Then we have the reed head of that Renishaw linear encoder and a few mounting brackets and bits and bobs. Then up top we have the second axis, the Y-axis I would call it, ball screw assembly. Again, another cooling pad, another Renishaw reed head, and the other blocks that we have for the Y-axis. And then we have the energy chain. Then all of these axes are lubricated by an automatic grease pump, and this is the grease distribution unit. So yeah, that's about it for the X-axis, I would say. Then we have the Y-axis, which is this one. So the Y-axis is an assembly like this. And what we have here is a set of rails down below and a couple of other rails for the Z-axis on the front. This, again, this has been made from granite, but what this has is, you can see it's got one piece there, another piece there, and a few connecting pieces in the middle. If I can get rid of this part. Oh, not that one. That one. Yeah. So you can see these connecting parts. These are also granite as well. So my granite supplier, they made these parts first, and then they lapped both ends together. These pieces of these inside faces, they've been lapped as well. So then they mount the whole thing together, and then they finally lapped where both of these rails sit together. So for this and that, and then they lapped this front face 90 degrees from this bottom face. So it's a very accurate setup. Then we've got these faces, which are again lapped, and this top face for where the motor sits. So we have a similar assembly here. Again, a piece of stainless steel plate. And then we've got the bearing housing, the coupling, the servo. Then we have the ball screw, again, the other end support. We have a similar setup for the Z-axis. The X and Y-axis, they have a 1 kilowatt, 6,000 RPM servo motor. And the Z-axis is 750 watts with a brake. Then we've got the energy chains for the cables and things like that. So that's about it for the, I would say the Y-axis. We do have another Renishaw linear scale somewhere here. And then for the Z-axis, we do have it as well. So let's get rid of that. Now let's talk about the Z-axis. So the Z-axis. Yeah, this is quite an interesting one. So let's get rid of this cover first. Right, and let's get rid of the Y-axis too. Okay, cool. So first, again, another piece of granite where the blocks sit on the granite, and then we've got the ball screw assembly. Again, similar setup, Renishaw reed head. Water cool sort of pad to cool it down, and various bits and bobs. Then we've got the spindle. This is a 60,000 RPM, 1.8 kilowatt automatic tool changing spindle, 1000 Hertz. This is water cooled, of course. And the tool taper is called T11, which is very similar to ISO 10. Very, very little tool holder. You can get it only with ER11, so up to 7 or 8 millimeter tool shaft diameter maximum. Then we have a mechanism here which would allow this top plate to be floating on a lower plate. So we've got two plates over here, and we've got a curve that's been machined on both of them, and these two have been lapped against each other to have a mating and matching surface. And what that does, it will allow me to basically rotate this spindle ever so slightly on this plate, and when you want to fine adjust and fine tune the straightness of the spindle center based on the actual Z-axis that goes up and down, and this is how I will achieve that. So that's for making the spindle parallel to Z-axis from this view. So you can imagine it will rock backwards and forwards like that, ever so slightly, of course. But we also have a similar mechanism for rotating it from this angle, where both of these plates will rotate at the same time. and we will use a series of grub screws that hold this whole thing together to fine adjust that. And once that's done, then we just tighten these bolts, and then it will stay in place completely solid, because all of these grub screws are holding it as well. Then we have this assembly on the right hand side. Because this is a turn mill machine, this will allow me to hold turning tools. So just one insert turning tool if I want to do some lathe work on this machine. It's assembly that would allow me to change the tools automatically for the lathe option as well. It's got a hydraulic 5-ton hydraulic cylinder up top, and then there's a sort of a spring mechanism that would release this tool, which I haven't really finished designing, but these parts have been made. So this side of it is fully completed. Okay, let's go and bring the rest of the machine. Again, display the whole thing. X-axis, stand. Yeah, we've got the electrical cabinet in the back, which is here. So we've got the Beckhoff drives, the power supplies. These are for the rotary axes, some EtherCAD modules, and this is the brains of the whole operation, which is the controller. Again, another Beckhoff computer, IPC. Okay, let's talk about, I would say, maybe the A and C axis. Right, okay, the A and C axis. So these also have been made with a very high precision in mind. So this is this assembly. Let me actually show you a section view. I would say that's a better way to show this. Yeah. Yes. Okay. This is much better. Right. Oops. Why doesn't stay? Apologies for this. Just remove it by one. Doesn't matter. Okay. So let's talk about the A and C axis from a section view. I think it's easier. Okay. So the A and the C axis, they have what I would call a torque motor setup. So there is no gearbox to drive these both axes. And there's a torque motor here and another one here. These are water-cooled torque motors. They have been manufactured by a company called CPC in Taiwan. I've used their other products for quite a few years, and I quite like the quality of their kit. Let me just create another section analysis so I can, maybe this one will allow me to, -100. For some reason it's not staying. Right. Oops. I can go back. Oh, it doesn't go anywhere. Right, okay. What I want to do first is to pin this so it will move. Okay, and pin, right. So it's not moving around, so I can explain the Z-axis probably a bit better. Right, okay, let's go back to this section view, or this one. Right. Why isn't it showing? That's why. Yeah, I was doing a Mr. Bozo over here, so okay, that's fine. Minus 100. There we go. Okay. Right. So the A and C axis, as I said, they have been manufactured from a single block of aluminium. Then the rear face was lapped, and then we got the front face where the bearing sits, and this front face and this diameter for the bearing. We got them jig ground on a jig grinding machine. And then there is a bearing, which is this one. It's a cross roller bearing, super precision bearing, extremely accurate. It's actually the most accurate one that you can actually find on the market. Then there will be an O-ring sealing this face, so no debris or anything can go near the bearing. It doesn't really need it. It's got plenty of protection on its own, but that's just another sort of peace of mind, if you like. Then we have, as I said, the stator for the for this axis, and then there's the rotor for this motor. This cavity, the space, is for a copper coil that will have coolant through it to cool this whole assembly down and keep the temperature regulated. Then we have this transmission shaft like this, which will go through the bearing, and it will hold on to the rotor as well. On the back side we have this, which is a 1mm glass disc, and this glass disc is the encoder for this motor, and that's the encoder read head right there. Then we have another bearing just to hold this end part of the shaft, and then we have a cap, which is a housing for this bearing, and then it closes the whole thing off. So that's your A-axis assembly. There are pretty tight tolerances for this shaft and also this housing, as I said. So this shaft has been ground very, very accurately. So the sort of perpendicularity and cylindricity and all of these different tolerances, they've been ground, most of them to 1 to 2 micron, which is pretty accurate for this size of part. Then we have this C-axis housing. This one is also made from aluminium, again jig ground. So we've got where this face sits against the bearing, the cross roller bearing, and also this diameter, they've been jig ground relative to where these bearings sit. Then we have the C-axis assembly. The C-axis assembly is a little bit more complicated because we have an automatic chuck here. This is by a company called System 3R. And what it does is it will allow you to change the workpiece using a pneumatic action. So this top pallet this is a pallet that you can exchange that very, very quickly by just push of a button, or in the future when I put a robot in front of the machine, completely automatically. So for the action of that pneumatic chuck, we needed a system to activate that. So from the inside of this transmission shaft, which goes through these angular contact bearings, again super precision stuff, goes through the motor and goes through this bearing. Then below we've got this assembly which will activate this pneumatic action. Right? So how do we do this? So we've got this pneumatic cylinder here, and we've machined these holes that you can see go all the way up to the side and up through here. So these are serious holes that intersect each other, and they go to this System 3R chuck. Then down below, as you can imagine, this whole top face will be rotating, and this is a 7,000 RPM or 8,000 RPM motor. So this is rotating very, very fast, and we can't have air channels going through this unless we use a big rotary joint or rotary union, which are very, very tricky stuff to make with high maintenance and again, quite expensive and not very reliable stuff. I've used them in the past and I don't really like them. I try to avoid using them whenever possible. And that's when I came up with this system. So I've got here this face and this part. What this part does is it has two separate channels, you can see here and there, and these will create an air pocket, and then we've got an O-ring there and an O-ring there. These O-rings will sit on this part of this shaft and this one on this part of this shaft, and what it creates is actually creating two separate channels or lines for pneumatic air to go through and then come up and go through the chuck. So when the chuck is rotating, this piece is like this, down, no action, no air is passing through. But when you want to change the part, this is a very big pneumatic cylinder. Again, it's got an air inlet here. So we push air through this. This will activate. This will go up, create a seal around this, and now I can push air from these side holes up to these channels and then release the pallet or the mechanism to hold the pallet. And then once you've changed the pallet, this whole thing goes back down, and then there's no contact between these two parts. So it's I call it a clever system because it allows you for this part to rotate at a very high speed without the need of a rotary union. Then we've got a copper coil around this space and very similar setup, another bearing. It won't have these two nuts. It will have a high-speed type single nut with a side lock. And then we've got the cabling issue. Now ideally for a setup like this, you would want to have the cables for the C-axis to go through the A-axis. Even though we've got a relatively large opening, we didn't want to use it like that and move all these cables through the A-axis. Reason being, because when you want to twist all of these cables in a relatively short distance, then the cables can break very quickly. So you need to change them frequently. So we didn't want to do that. And we ended up doing something that I really disliked, but was necessary. And we used an external system. So this will have a conduit fitted to it, and then the other side of the conduit will go onto another sort of gland over there, and then we will have a conduit sort of dangling down below. It's not pretty, but also I didn't make this machine to look pretty. It's yeah, the looks of this machine is not pretty at all. It's quite industrial and without a focus and attention to sort of looking nice, but it is quite functional, and functionality was what I was after, not not to make it look like a very nice product. So it's functional, reliable, because obviously these are all fixed. It's not rotating, things are not twisting. We will have only a 45-degree 45-degree movement for this gland, as opposed to an almost 270 degrees twisting motion for the cables up top. So it will have a much longer life than if I wanted to move the cables through here. With that said, I've kept this hole open so that in the future maybe we want to use something different in through this, and feed something different through the middle of this A-axis, so we'll have that capacity. Okay, so let's go back to the other parts. I probably should get rid of this section view. Okay, right. Right. Then we have the tool changer mechanism. The tool changer is mounted on an arm. This moves back and forth like that. It will have its own electrical actuator. I think there's a joint, something missing here. So this is an electrically activated actuator with a spring mechanism to push it all the way through. Then we've got one of these hollow shaft gearboxes with probably about 1 arc minute of backlash, which is more than accurate than what I need for this axis. Then we've got this sort of wheel setup with 28 pockets for tools. And this is the tool holder. I've got here a Renishaw RMP 24 micro, which is the smallest wireless probe you can get in the world at the moment, actually. So this will go onto the spindle, and we will have an automatic tool changer with 28 pockets in the magazine. Let's look at all the sheet metal work as well. So these are all the sheet metal side of it. So once this is all the way back over there, we will have a polycarbonate guard around it. I probably should bring the Z-axis cover as well. Just bear with me. Right, okay. Looks a little bit better now. As I said, looks were not the main concern for this machine. So this is the C-axis. As I said, it will rotate like that. The A-axis, I don't think I showed you that. Let me just go to this assembly and unpin this part like so. Okay, it should rotate. So let me just bring this down. Right. So this will rotate almost to, I think, something like this. Yeah, definitely like this. And then from the other side to somewhere around here. So it's got about 180 degrees of travel. Most of the time it will be like this, where the spindle comes and starts sort of milling, or if you've got some turning application, the other tool holder will come in and you will do some turning like that. It's good to say that the spindle actually will, you can shift the spindle up, so you can just unscrew this or loosen this, and then you can just like push the spindle up and then hold and then tighten this in place. Then you've got this tool holder for your turning tools. So if you want to do some turning, put a thread on a part. We will eventually have a space over here for where you can park probably 2 or 3 of these different tools for your thread cutting and for your grooving or cut off or things like that. So we will have eventually 3 or 4 different tool holders for the turning tools. Then we've got the spindle. The spindle actually, even though it's pretty small, it is a closed loop spindle. So we have an encoder. So if you want to do some guilloche patterning and things like that, you can use a single edge tool on this spindle and then hold it in place, because it's got 1.8 kilowatt and it's water cooled, so you can hold it firm and steady to do some pattern and guilloche pattern machining. So this will be most of the times like this, or sometimes like that. Then obviously you've got this fixed table where you've got another set of these. So if you're doing a lot of 3-axis work or some roughing, you wouldn't want to put it on this table, because obviously this will put stress on the bearings and things like that. So for 3-axis work, you can just use this table, or you can just get rid of this. If you've got, if you need a vise, you can just mount a vise. Or just a part directly onto the bed itself. So there's various options that you can use this table for. At some point I will probably make another assembly of another table, a 90-degree table, and then with a bigger, thicker plate joining both tables together, so you can put a massive part about 400 by 200 millimeter on the machine, and then CNC machine that in a 3-axis way. But obviously this is a pretty accurate machine, so that part with that massive size would be pretty interesting to do. So it's got a lot of versatility. That's the other side of that conduit, so that's for the cables. Then we have this polycarbonate system that goes up and down, so it's just a shield. It will have, again, actuators to activate it. It won't be manual. So when the machine wants to do a tool change, this will go down. It takes about 1.5 to 2 seconds. And then this will come in, and then the spindle comes here. That's where the position number 4, for example, is. That's where you can change your tool. So it picks one of the tools up, or basically now it just drops its current tool, goes up. Then this one rotates like that, brings the other tool, and then this can pick it up and then go back. And then this will go back like that, and then this one comes up. So that's the sequence for your tool changer. This is just a grease pump. Then underneath we've got the coolant tank, which has got separate pieces, and the coolant pump. So it's got one of those sort of different level filtration systems. Then the coolant tank is also isolated, thermally isolated. And by that I mean there's isolation panels, or insulation panels rather, insulation panels all the way around the tank, so the temperature of the coolant will stay stable, and obviously the coolant will go through another chiller as well, so we will have a chiller separate for the coolant, and then that goes back in. Oops. Okay, then we've got another drawer like here for different filters. So we've got 2 micron filters for the coolant, and a few other sort of solenoid valves and things like that will be mounted over here. Then the whole machine will go into another double glazed window type of enclosure, so it won't have any interactions in terms of thermal interactions with the actual environment, and that chamber will be cooled down by an AC unit. So effectively we've got one chiller for the spindle and the A and C axis, one for the ball screws and the linear guides and all those cooling pads that I showed you for all of the X, Y, and Z axis and the relative ball screws. Then we will have another chiller for the coolant, and then we have an AC unit for the whole chamber. So 4 chillers effectively working together to keep the temperature relatively stable. We've got other mechanisms. For example, there's another spring mechanism. Then we've got these roller covers, way covers. There's another mechanism for way covers in the front, so this will be covered up as well. It won't be exposed to elements. There's a lot more to tell you how, for example, this whole thing is floating on this frame, so it's not actually connected. As I said, it's isolated, mechanically isolated. But I don't think that you will be interested in all of those little details. If you are, please leave a comment on the video on whichever platform you're watching this, and I will try to either answer through the comment section or just explain it in further videos. But for now, thank you for watching, and if you're watching this on YouTube, please consider subscribing to the channel, and I would appreciate it a lot, and I hope I will catch you in the next one.